Hello, I'm Paul Beckwith. I'm with the Laboratory for Paleoclimatology at the University of Ottawa. In this video and in several additional videos, I'll be discussing methane. So this particular video, I'll talk a bit about the molecule, a bit about so-called methane hydrates or methane clathrates or gas hydrates. They're all the same name. Actually, gas hydrates, other gases can become hydrates, but I'll talk about methane in this particular case. And I'll talk about some of the distribution of methane on the planet, concentrations, how they're changing. And then in the next video, I'll talk about some very, very recent papers on methane in the Arctic and how climate change and sea ice is affecting the methane in the Arctic. So the methane molecule is basically a carbon atom surrounded by 4 hydrogen atoms. It's a gas in the atmosphere. It varied between about 400 or about 350 and 700 parts per billion over the last million years or so, as we know from recording bubbles, measuring gases in bubbles in ice cores. And now we're pushing numbers of 1,850 parts per billion. We've seen numbers in the upper atmosphere much, much higher than that, 2,500 parts per billion, even approaching 3,000 parts per billion. Methane is a very powerful greenhouse gas, much more powerful than CO2 on a molecule per molecule basis. So this is the molecule in the gas form. There's now when you get high pressures and low temperatures, for example at the seafloor, then the methane can be trapped in hydrate form. So basically the water molecules consisting of one oxygen, the red molecule, and 2 hydrogen atoms, the white molecules, form this lattice structure, frozen water, around a methane molecule, which is the one carbon atom surrounded by 4 hydrogen atoms. Okay, so this is a methane molecule. It's surrounded in a lattice of water, frozen water molecules. Of course, as the temperature rises, or if the pressure is released, then the frozen lattice will thaw, and that will release the methane. And the volume of this material will expand about 164 times. So getting back to methane, okay, CH4, okay, it's basically the main component of natural gas. So if your house is heated with natural gas, about 90% plus is actually methane. It's abundant on Earth, so it's an attractive fuel. When you burn it, it produces less CO2 than coal and oil. But the problem is when it leaks, then it causes a lot of warming. It's a very powerful greenhouse gas. So it's found both below the ground and under the seafloor. It accounts for about 20% of the radiative forcing of the greenhouse gases. So it's not warming as much as CO2 at the moment, but it's causing a significant amount of warming. So I'll talk about, there's lots of information on the molecule itself here. We'll just focus on where are we here? We'll just focus on the greenhouse gas properties, the atmospheric methane. So methane's, it's created near the Earth's surface by microorganisms. The process is called methanogenesis. And then the methane is carried up into the stratosphere by rising air in the tropics. Most of it is in the lower atmosphere, which is the troposphere. What removes it from the atmosphere is OH minus radicals, known as hydroxyl radicals. So it's oxidized and therefore converted into CO2 and water and removed, there's lots of methane in clathrates on the ocean floor and on the Earth's crust. And if organic matter decays in the presence of oxygen, that produces CO2. If there's no oxygen, it produces methane. The global warming potential is 34 compared to CO2. That's over a 100-year time period. And it's 72, actually it's 76 over a 20-year time period. That's incorrect. Up until about 2007, it had flattened off, and then it started a strong uptick here. Interestingly, 2007 was a sea ice minimum, as was 2012. So the clathrates, there are significant clathrates on the ocean floor and in the sediments. And what else was there? Okay, so we'll go on. So getting back to the clathrates, you can also call it ice that burns or fire ice. So gas hydrate, methane hydrate, or methane clathrate. So it's CH4 and it's surrounded by 5.75 H2Os. Okay, so it's a naturally occurring solid form, solid material, ice-like substance, combines under high pressure, low temperature. So when you get warming, it can be released, go up into through the water column, up into the atmosphere if the water is shallow. So where is this stuff? Okay, well, this is an interesting, this shows some of the distribution of it. Now, gas hydrates have been recovered from the blue triangles, and from the red circles, gas hydrates are inferred. So these are hydrates worldwide here, and you can see that the distribution of them. They're on the continental margins where the water is fairly shallow. In order to the so-called gas hydrate stability zone, GHSZ, is typically around 400 to 500, 550 meters deep. And this is the area where the water pressure and the water temperature are such, the water pressure is high enough, the water temperature is low enough, such that methane being released from the sediments then would form these hydrates. It would be trapped in the frozen hydrate. So these are regions, so there's extensive regions where this hydrate exists. Okay, so in terms of the global distribution of atmospheric methane, here we go from 1996 to 2005. We go in latitude from the South Pole to the North Pole, and this is a concentration of methane. The units are nanomoles per moles, or in other words, parts per billion, molecules of methane per billion molecules of air. So what you can see is that in the southern latitudes, it's lower, and as you go up and approach the Arctic, it gets higher and higher. And you can also see that it's increasing. It's increasing through time. So most of the sources are up here. Most of the sinks are here. It's a lot drier. There's less sources here. A lot of sources here. It's a lot drier up here than it is, say, at the equator. So you can have a lot of wetlands, a lot of methane emission at the equator, but there's lots of water vapor in the atmosphere, therefore there's lots of OH-, therefore the methane can be broken down quickly at the equator, whereas as you go up into the high Arctic, there's a lot less water vapor, a lot less OH-, so the methane can stay up there for longer, and this is where the sources are, the permafrost and the sediments under the sea. So the methane is rising, and as the Arctic is warming much, much faster than the rest of the planet, then the risk of the methane increase from the Arctic can increase. So this ends in 2005. The next image here, this shows a similar diagram, but this is 2005 to 2014 now. So what you can see is around 2007, there was a large increase in methane. Okay, so this is, like I said, this is a year there was a minimum sea ice, You know, the water's warmer, there's no ice, there's more mixing of the water, there's many reasons, but there's more methane coming up in the Arctic starting in about 2007. Just for interest, this is a similar diagram with the atmospheric CO2, 1997 only to 2008, and you can see how it's rising, but you can also see the distribution. So it's lower, it's basically lower in the southern hemisphere. As you go up into the northern hemisphere, up into the Arctic, the CO2 levels are much, much higher, and this is because the sources are much greater in the Arctic, and you can see this rise up here. This only goes to 390. We've approached 410. And this is parts per million, micromoles per mole, or parts per million. One part per million is 1 molecule of CO2 per million molecules. So this is the CO2. So this, so it basically, methane, the main greenhouse gases are, people talk about CO2 all the time, you know, which is very important, long-lived greenhouse gas. Methane is a very, very powerful greenhouse gas compared to carbon dioxide. The levels are lower in the atmosphere. It's only causing about 20% of the effect of what the CO2 is doing, but the levels are rising extremely rapidly, and there is a large risk of large releases of methane, and that will greatly accelerate the warming that we're seeing. Now, there was some very recent papers that have come out that talk about methane emissions, the effect of climate change on methane emissions from seafloor sediments in the Arctic Ocean, a review paper. People are starting to study methane more and more. This paper is on seepage from the Norwegian margin after this ice sheet's left, and the effects on methane. This is simulating methane release on the eastern Siberian Arctic shelf. These are all papers that are out in the last month or so. The warming of near bottom waters on the Laptev Sea shelf, and so on. And some of the new methods, like using LIDAR, which is laser radar, to monitor methane in the Siberian permafrost, and also the idea of using unmanned UAVs, drones, to measure methane in the atmosphere. We need to find out a lot more about the distribution of methane on the planet, and in order to accurately assess the risks. You may recall that Peter Wadhams wrote a paper a few summers ago with an economist, and they looked at the effect on humanity, on civilization, if there was a release of 50 gigatons of methane, either over a year or two or over 10 years, and they found that the effect on the global economy was something like $70 trillion. So we need to take methane extremely seriously. So I'll end this video here. Thank you for listening, and please watch the next video, which I apologize is a bit more technical, but it's about recent scientific work in the Arctic as far as methane is concerned. So thank you.